Welcome to this session on the challenges of scaling static vulnerability discovery. My name is Fabian Yamaguchi, and I'm the chief scientist at Shift Left. And so what we're going to be talking about today is essentially some experience points, some things that I found out in the last 5 years where I led an effort on building a static analysis pipeline. And so what that means is what we wanted to build was a program that would receive other programs and would point out all of the vulnerabilities in that program. And the additional difficulty was that this was supposed to run in CICD, meaning whenever a developer wanted to bring a change in, we would want to run our static analysis and find all the bugs, all the vulnerabilities before they were actually merged into the master branch. And this talk, I'd say, summarizes the learnings on the way. And I want to begin by talking about why we can't really get around static analysis, because I feel that many people are asking themselves these days, hey, static analysis is so tricky. Why should we do that at all? And if you have not heard of static analysis, then I'll also be briefly telling you today what that is. We'll then be talking about the key challenges when you want to bring static analysis into CI/CD pipelines, and our approach of addressing these challenges. And then finally, this is not so much about just telling you how good our analyzer is. I'm actually going to also point you to our open source work, so you actually have code to work with if you ever find yourself in the situation of wanting to build something similar. So there you will also find quite a bit of information in the form of code that you can make use of to make your life simpler on that when you're trying to do that. So let's define the goal. So ideally, we would want to have a system that just accepts any program that you give it, and it will point out all the vulnerabilities in it and be completely right about that. And we want that to work within 1 to 20 minutes, maybe. I mean, that seems, 20 minutes might already be a bit much, but you get the idea. So that we can integrate it into CI/CD. And we wanted to work across all the relevant programming languages with all the relevant libraries and all the relevant frameworks. As you can see, that's a big ask. That's a big task that we're dealing with here. And the bad news is that even the theory, like from the 50s, already tells us this is actually not going to work, right? What I mean by that is we aren't going to build a perfect system that always finds all of the bugs, reports nothing that is flawed, and so on. And this goes back to like a fundamental theorem in computer science known as Psoriasis Theorem that says that pretty much like any property of a program, as they say, a non-trivial property, is undecidable, meaning you can't really write a program that will tell you about that other program, whether that property is given or not. But what does that mean in practice? So first of all, this is a statement about how bad it gets. It's not necessarily a statement about your average case. So you can still end up in a situation where you can say with 100% certainty, this is a vulnerability, and that's that. But what it means is that you can always have cases that are just too tricky, where you can't tell. And in practice, it also means that if somebody tries to sell you an analyzer and says that that thing has no false positives and it has no false negatives, then that's not true. That's simply not doable. So there's always a trade-off between false positives and false negatives, meaning sometimes you find things that well, you point out things where you think that they're vulnerabilities, but they're really not. And sometimes you just miss a vulnerability that you would have liked to catch, but you just didn't. On a side note, what that means, by the way, this whole theorem that I was pointing out, it means that building detectors for something like malware or backdoors is actually really, really tricky. Because in this case, you're trying to reason about a program that can be arbitrarily hideous. So the person on the other end can say, I want this program to be tricky to analyze. And then it will be tricky to analyze. For vulnerabilities, it's a bit better because at least the programmer doesn't have the incentive to make the code really hard to analyze. But it still means that if the code is written in such a way that for a human, it's already hard to reason about it, it usually means it's also hard for a computer to reason about it. And this can already be in the language. So for example, analyzing JavaScript is a lot harder than analyzing Java simply because of properties of the language. So when you're dealing with a situation where you can't solve a problem perfectly, but you have to do it anyway, that's where you enter the realm of computer engineering. So you can really think of this as a computer engineering task. And that means trade-offs. We want to build something that's good. It's not going to be perfect. And what it should do is it should be able to check the code for properties that are highly indicative of vulnerabilities. So if those things are true, then you're very, very sure that this is something to at least look at. And then secondly, you want to know what to compute and what not to compute. So you could do a lot of detailed analysis to make sure that certain kinds of false positives are not going to be detected. But in the end, this might not even be worth it, and it will come at a huge computational cost. And so that's one of the trade-offs that you need to make. To be fast, really. So you want it to be fast. Another thing that's really important is that it's deterministic, meaning if you analyze the same code twice, you get the same results. Sounds simple, it really isn't. And then finally, you want as few false positives and as few false negatives as possible. So in general, you can take two routes to do this. You can go for static program analysis or dynamic program analysis. And static analysis means that you analyze the code. So you have a program that reads the program as a human would do. And then there's dynamic analysis, which means you execute the program and you see what it does. And in reality, this is a spectrum, meaning if you have a dynamic analyzer, then usually at some point it will also do a bit of code analysis to see how to proceed. And if you have a static analyzer, you might start emulating the code. So you could say, well, you're kind of executing it just on a custom interpreter. So this is a spectrum. This is not like something is completely dynamic or completely static. And there are even things like symbolic execution, where some people say it's static, others say it's dynamic. But right now we live in a time where the current trend is dynamic analysis is a lot more popular than static analysis, and especially a technique known as fuzzing, which essentially means that you run the program and you generate input that's likely to cause undesired behavior, and then you try to monitor for that and see if it happens. And that's a pretty cool technique because you don't need any code. You're actually not going to read the code, right? So you can do that black box. Of course, if you want to be more efficient, you will have to somehow analyze the code a little bit, but not so much. And when you do find something, then you already have an input that will trigger this behavior. So that's nice. So that doesn't mean that all of the things that you find there are going to be vulnerabilities, as in you have no false positives. But it does mean that you're not going to be finding things that can't be triggered at all. And another nice thing about this dynamic approach is that it's easy to build something that works across programming languages because you're not going to analyze the code anyway. But there's also a disadvantage to talk about, which is coverage. So the problem is it's often a lot easier to find code that looks vulnerable, but it's much harder to actually generate an input that would trigger that. And so dynamic analyzers, since they're limited to things that they can actually trigger, you kind of opt towards more false negatives, meaning there's a lot more that you miss. So coverage is the central problem for dynamic analysis. And so in the end, you spend a lot of time finding all of the different ways in which data can be passed to the program. And that's a lot of work. And so increasing coverage really is the central problem to dynamic analysis. Now, the big problem when running this stuff in CICD, though, and that's our goal here, right, is that the time that the analysis takes actually does not just depend on your dynamic analyzer, but it depends on the program that you're analyzing. And so that's problematic because it means if the program you're analyzing is slow, or let's say it even runs into an infinite loop or it somehow hangs on certain inputs, then your analysis is also going to be slow or run into an infinite loop. So in practice, all you can do then is you can say, well, if I've had it running for a few minutes, then I better stop it. But that means that the entire analysis becomes non-deterministic. So you get different results depending on when you ran it, in which order it was executed. And that's problematic. Now, static analysis really shines here. It doesn't depend on that runtime. And you can see a lot more. Problem is, it opts more towards false positives because you don't always know whether something can actually be triggered. And even if getting the data to the vulnerability happens via exotic means, you'll still be able to find the vulnerability. So in short, for an arbitrary program, a static analyzer won't be able to tell you whether it halts. But for a dynamic analyzer, it's much worse. If the program does not halt, the analyzer does not halt. And so in the CICD context, that kind of means, okay, doing dynamic analysis in CICD, that's going to be impossible to very, very tricky. So vulnerabilities covering CICD pipelines, pretty much it means we have to do static analysis. So even if static analysis is tricky, and it is tricky, we're not going to really get around it. And so, let's look into it, whether we like it or not. And so these are the key challenges that we found doing this over the years. So overall, it's a matter of scalability. And often you run into scalability issues that you wouldn't see in a lab environment, but that become immediately apparent as you start dealing with real masses of customer code. And so what does scalability mean? Well, typically, it's about a system's ability to deal with ever more and more work that it gets. But in a more general sense, you could say it's about the capability of the system to grow as some sort of demand increases. And there are different demands for the system that increase. So one thing that increases over time is just the vulnerability types to check for. So you remember we wanted to do this for all sorts of different programming environments. What you're going to have to do now is you're going to have to model what the typical vulnerabilities look like for each programming environment. And so you need something that allows you to include an ever-increasing amount of aspects to the code that you can consider in your analysis. Second thing we mentioned is languages, libraries, and frameworks. So if somebody adds a new language that's become popular, yeah, that's something that we're going to have to support. And you're going to have to deal with like 10 to 20 languages. So the system better be able to grow into that dimension as well. And then, of course, there's just program code and submissions. So as your system becomes more popular, as you have more customers, they're going to be submitting more code for you to analyze. And it can also happen that what they submit is just one large program, and you need to be able to deal with that as well. All right, so let's deal with the first one, which is the different aspects of code that you need to model. And I know that sounds pretty abstract, so I'm going to give you an example. So let's take a classic deserialization vulnerability, as was popular a few years ago in conjunction with the Jackson data bind library. So here, what happened was that if an attacker could provide input that would be passed by the Jackson data bind library and a few other conditions were met, then that attacker could actually execute arbitrary code. And so the exact conditions were a vulnerable version of Jackson data bind needed to be installed, so certain version number. Then the attacker-controlled input needs to be deserialized in a call to a function called read value. And then finally, default typing needed to be enabled via a call to enable default typing. And so if you look at it in code, this would be an example. So you have request.body, that's something that the attacker controls, like an HTTP request body. It's passed into read value. And what we don't see here is that call to that function to enable default typing. And so, that's where the call is now. And so if you want to detect something like this, what you're dealing with is you need to be able to model the program dependencies. So you need to know about Jackson data bind, the syntax of the program, data flow, and method invocations, all of these things. So those are all different aspects to the code. And then in the end, you want to encode that in a nice query, something like this that just says, well, I want the dependency to be Jackson data bind. The version should be 2.8 and something. And there should be a call to a function named enable default typing. And then finally, there should be a method named read value where the first parameter is reachable by something that comes from HTTP's servlet request, as in it is an HTTP request that the attacker controls, right? So here in that query, all of these different aspects come together. And now you can imagine the first question is, how do I build something that will allow us to bring in new concepts, things like calls, things like parameters or reachability or dependencies, these kinds of things. How do I build something like that? So the question is, how do we provide a code representation multifaceted enough to deal with the complex combinations of program properties that make it vulnerable? And the idea is actually quite simple. You have a lot of different graph representations of code, and well, most information can be represented well in graphs, or well, not so well, but you can represent them in graphs. And it happens to be that for program analysis, you find a lot of graphs already by default. So you have things such as syntax trees or control flow graphs. You have the type hierarchies. You have package hierarchies, things like that. And so can't we merge all of these together into one data structure that we then use to define our queries on? And yeah, we can. So there's a concept known as a property graph. This is actually the native data structure used in graph databases. And the key ingredient here is that you have labels on the edges of that graph. So that means that you can represent multiple different relationships in a single graph, right? And so that's what we built. We built a code property graph meaning you have all these different aspects in the single graph, and you can transition from one representation to the next by following edges in that graph. And yeah, today it's this like a multi-layered representation. So next up, what about the increasing number of languages? And so here the core ingredient has been known for a very long time. It's called intermediate representations or intermediate languages, meaning take whatever code you have, analyze it, and map it to a language that is now independent of that source language. So we could have just, and we actually tried that for a while as well, taken a compiler and used their intermediate representation, because compilers already do this. They have all these language front ends, then map to an intermediate representation and do all of their analysis on that. But what we found was that these intermediate representations are all built with a concrete goal. And for compilers, that's code optimization and just code optimization. And so these are actually pretty ill-suited for code querying, because a lot of the information that was nicely available in the source code is now gone. So if you look at LLVM bitcode, then you'll see it's very lengthy. It looks more like assembler. So it's not at all something that you can query easily. And it makes it very hard for programmers because they would have to translate the code in their head to this intermediate representation in order to write queries. So that's a no-go. So we designed an intermediate representation, especially for code querying. You can take a look at that. It's mostly open source. So we have layers that are closed source, but a lot of layers are open source, like base layers. And you can find it at cpg.yearn.io if you want to get an idea of what's in there and what's not. And in the end, what it means is we'll translate code from different languages to this representation, and then you can write language-independent queries on top of that representation. And then finally, we wanted to talk about what happens when you have more code and more submissions. So in general, more code means more computation. So if you find a system that seems to always take exactly 7 minutes or something like that to give you results, then usually that means that it just runs with a timeout, and that means it's not deterministic. Now, we didn't want that. Being deterministic is important, otherwise you constantly get changing results. So what that means is that if the amount of code that you need to process increases, then you need to compute in parallel to be done in the same amount of time. So the key here is to define your analysis steps and then really ask yourself, which of these are independent? Which of these can I run in parallel? And then inside of these steps, what you'll find is that you have analysis algorithms, and those are usually not designed so that you can just, decompose them nicely into problems that you can solve independently and then put everything back together, so like in a MapReduce style. So a lot of work actually here then goes into taking the algorithms and creating something similar, maybe an approximation to that, that can be computed in individual tasks that can be solved in parallel. That's a key direction to take here. And if you want to get an idea of what I mean by that, I mean, that could be an entire talk by itself, but take a look at our open source data flow engine. That's an example of where we took like a pretty classic approach, and we just made sure that we can approximate that, but do that with parallel tasks. What we built then to make all of this a bit easier is a pass mechanism. So when you have one of those code property graphs, you can define a task on top of it, which we call a pass. And this these passes, they can run in parallel. And each of the passes creates an overlay, which is like a new part of the graph. So you add information to the CPG by creating this new layer. And then there's a reduction step. So it is a bit like a MapReduce mechanism where you join together these overlays created by the individual passes to create one new layer. Yeah, and that's an overview of what we've created here. And if you're interested in this kind of work, please check out our open source code analysis platform, Yearn. It implements all of these core concepts that I spoke about today. Started off in about 2013, so even before the company. And today it gives you an interactive programming shell for vulnerability discovery. And it's based on Scala, so it's a Scala shell more or less. It allows you to analyze code in many different languages: C, C++, Java, JavaScript, JVM bytecode, LLVM bitcode. Now we also have Kotlin available and even binary code, which was recently added. Yeah, so come join us. And there's a collection of queries for you to learn the language. And with that, I'm ready for questions. And yeah, this here is the link to the analysis platform that I just spoke about.